Here's another kind of a mysterious problem that I want you to get some practice at. Claim Q adjoins, say, square root of 2 and square root of 3 is the same as Q adjoin square root of 2 plus square root of 3. I claim this is true, okay? As one example of something I could prove in a similar vein. There's lots of examples you can make like this, okay? The book does this example, I believe, something similar in chapter 20. How do you prove this? Proof question mark, because it's unclear how to go about proving this. We're trying to prove the equality between two fields. These fields are sets. So you'd ultimately be trying to prove the equality of these sets. Now, we've already written Q adjoins square root of 2 and square root of 3 in this way. So one approach to trying to prove this, I'm using different letters now, would be to try to say, okay, Q adjoins square root of 2 comma square root of 3 is this set. So to prove the equality of these two things, I guess I'd have to show this is equal to the same set. That's one approach to try to prove it. It's not the most efficient approach. I want to try to come up with a more efficient approach to illustrate for you. That's based on the definition of field extensions like this, where we adjoin roots. That's the definition. By definition, this is the smallest subfield of the rationals containing all the smallest subfield of the reals containing all the rationals, square root of 2 and square root of 3. By definition, this is the smallest subfield of the reals containing all the rationals, and this one number, square root of 2 plus square root of 3. But again, it contains more than just that one number added. It contains infinitely many more. How do you use the definition to prove these are equal? One inclusion is definitely easier than the other. This inclusion is the easy one. Prove that this set is a subset of this one. How do you prove it? Use the definition and the fact that this thing is a field. This thing, again, is the smallest subfield of, for example, the reals, as one example, simplest example to take, I guess, containing all the rationals and the number square root of 2 plus square root of 3. This is the smallest subfield of the reals containing all the rationals and square root of 2 and square root of 3. All right, here's the punchline though. Since this thing is a field, it's closed under addition. Since it contains square root of 2 and square root of 3, it therefore also contains square root of 2 plus square root of 3. That's the smallest one. Therefore, this must contain this. Say that again. Let's write it out. Since this is a field, in particular, it's closed under addition. Therefore, it contains square root of 2 plus square root of 3. It's got square root of 2 in it. It's got square root of 3 in it. It's a field. It's closed under addition. Therefore, it contains their sum. Since this one was the smallest subfield of R containing all the rationals and that sum, it must therefore be a subfield of this one. Done. It's kind of a subtle argument. This is a kind of argument I want you to get. The harder proof is the other inclusion. But you still use the definition of these field extensions, where you take the rationals and join these roots. Once again, this thing is the smallest subfield of the reals containing Q, n square root of 2, n square root of 3. And this one is the smallest subfield of the reals containing Q and the sum square root of 2 plus square root of 3. I'm trying to show this as a subfield of that. It would be enough to show this thing contains square root of 2, and it also contains square root of 3. And then therefore, this one being the smallest such field containing all the rationals and square root of 2 and square root of 3 would mean this is a subfield of that, because it's the smallest. So I'm about to try to show that this thing contains square root of 2 and square root of 3. But it's tricky. Certainly, again, this thing contains square root of 2 plus square root of 3. And it is a field. It's going to contain its reciprocal as well. But now let's try working with this reciprocal and seeing if it any interesting conclusions can be made from it. One thing we could try to do to deal with this reciprocal, to find the multiplicative inverse, is we could try to, in a sense, rationalize the denominator here, multiply by square root of 2 minus square root of 3. You could also try to multiplying by square root of 3 minus square root of 2. But if I don't want to change the value of this number, I've got to do it on the top as well. Let's see if something magical happens after doing this rewriting of this number here. If I FOIL out the bottom, I get square root of 2 times itself is 2. Yes, the outside and inside terms cancel, which is why you do this trick. Last times last will be minus 3. Negative 1 here. So we get, in the end, square root of 3 minus square root of 2 is the multiplicative inverse of square root of 2 plus square root of 3. Isn't that interesting? May want to check it by multiplication. Square root of 2 plus square root of 3 times square root of 3 minus square root of 2. FOIL this out. You get square root of 6 from first times first, then minus 2, then plus 3 from inside times inside, and last times last is minus square root of 6. Those cancel, and it simplifies to 1. You can check it with your calculator too, okay? You can type in square root of 2 plus square root of 6. Okay, let's go ahead and do it. Type in square root of 2 plus square root of 3. Oh, wow, close to pi. Not equal to pi, though. 1 divided by that is its reciprocal. That should be the same as square root of 3 minus square root of 2. 3. Square root of 3 minus square root of 2. Yeah, okay. It worked. Kind of amazing, but it worked. Okay, but how is this helpful? So what this is showing is that this difference is in this field. Yes, it is the multiplicative inverse of square root of 2 plus square root of 3, but it's also showing it's in this field because this is a field. The multiplicative inverse of this element's got to be in it. And then you stare at this long enough, you realize, hey, if I added these two things, which are in the field, the result would also be in the field. What happens when I add them? Square root of 2 plus square root of 3 plus square root of 3 minus square root of 2 gives me the square root of 2's cancel, 2 square root of 3. And if I divide all this by 2, it gives me square root of 3. These things are in the field. I divide by 2, it's still going to be in the field. 1/2 is in the field. Square root of 3 is in the field, is what I just verified. What about square root of 2? How about instead of subtracting, adding, we subtract? and probably divide by 2. The square root of 3's now cancel, and you get 2 square root of 2 over 2, which is square root of 2. Therefore, square root of 2 is also in this field. And that does it. I verified that square root of 3 and square root of 2 are in the field, this field. By definition, this field is the smallest subfield of the reals containing all the rationals and square root of 2 and square root of 3. Therefore, it must be a subfield of this one, if this one contains square root of 2 and square root of 3. But I showed both inclusions. They're actually the same thing. They're actually equal. Where are we going with this? Besides just playing around with adjoining roots to the rationals, we're going ultimately toward Galois theory starting next Monday, and trying to understand a little bit of Galois theory. And what's Galois theory for? The Galois theory ultimately is for, well, one purpose is proving that quintics and higher degrees are not solvable by radicals. There's no, there's a quadratic formula, there's also a cubic formula, there's also a quartic formula. There's no quintic formula for solving a general quintic. It's not clear how we're going to get there. And in fact, we don't completely get there. We only touch the surface of an iceberg. But that's the purpose of all of this. Let's end class, our final 2 minutes, thinking about one other issue related to these examples. When you're thinking about these kinds of examples, you often make what's called the tower of fields. It's similar to a subgroup lattice for groups. There's the rationals. Well, I made it wrong already. Here's the rationals. Q adjoin square root of 2 and Q adjoin square root of 3 are field extensions of the rationals that, as vector spaces over the rationals, have dimension 2. A basis for this one is 1 comma square root of 2. A basis for this one is 1 comma square root of 3. In this tower of fields, we put that number next to the line segment, indicating the dimension of this thing as a vector space over this thing. They both have dimension 2. This has also got another name. It's called the degree of the extension. You're going to do some reading about it very soon. Q adjoin square root of 2 comma square root of 3, which we've just verified is the same as Q adjoin square root of 2 plus square root of 3, is a field extension of both of these. And it turns out it has degree 2 in both cases. We also saw, I mentioned without proof, that this thing has dimension 4 over the rationals. If I draw a line like this, I'd put a 4 next to it. Why? I mentioned because 1 square root of 3, square root of 2, and square root of 6 forms a basis. It's not a coincidence that when you multiply the numbers along each path through the lattice, you get the entire final dimension. 2 times 2 is 4. It's not a coincidence. It's a fundamental theorem in chapter 20 or 21, one of those 2 chapters, in the newer edition of the book. That has very important relevance for Galois theory. It also implies that evidently this number, square root of 2 plus square root of 3, since these are equal, must be a root of a 4th degree polynomial, irreducible polynomial with coefficients in Q. It must be. What polynomial? We'll save that for next time.